if we have a nozzle attached to a garden hose, can we find the speed of the water in the hose and the nozzle, given enough other information? My contention is yes, we can, and we shall do it right now. From the problem statement, we have a flow rate of 0.5 liters per second. That's a volumetric flow rate because it's a volume per time. Our diameter, actually we have a radius of the garden hose. It's interesting. Normally you're given diameters of hoses, but here we have a radius of 0.9 centimeters and a diameter of the nozzle of 0.5 centimeters. If I want to get the radius of that nozzle, then that's half the diameter, 0.25 centimeters. All right, we want the speed of the water in the hose. Since we know the volumetric flow rate, we can say that the volumetric flow rate is equal to the cross-sectional area times the average linear speed of flow, Q equals AV. We can solve this for V by dividing by A on both sides, and we get V1 is equal to Q over A1, which we can substitute in for what our cross-sectional area is of a circular cross-section. That's pi r squared. We get Q over pi r1 squared and plug in our values, doing some unit conversions to change from liters to meters. And we're left with 1.96 meters per second as the average linear speed of flow in the hose. Now, how about the nozzle? We would think that the nozzle should have a faster average linear speed of flow because that's the point of the nozzle, right? To speed up the flow. Let's see. Q2 is equal to A2V2. V2 is now equal to Q2 over A2. We can plug in as before, do the same stuff. Or if we want, we can use our continuity and say that A1V1 is equal to A2V2, assuming that we have constant density between these two. That lets us solve for V2 in terms of V1 and gives us V2 is equal to V1 times the ratio of their cross-sectional areas A1 over A2. Now we can say that my average linear speed of flow in the nozzle, V2, is equal to the ratio of their areas times V1. With numbers in there, it looks like this. The pi is canceled, and we get a final average linear speed of flow of 25.5 meters per second. That is indeed a lot faster than it was in the hose, which makes sense. You narrow the aperture, so you get faster linear speed of flow, and you can shoot your water farther with your nozzle.